Talks, and our next speaker is Wai Tong Chung from Stanford University about accelerating high-fidelity combustion simulations with classification algorithms. So, Mike is all yours.
Hey there. My name is Wai Tong Chung, and today I'm here to talk about my work accelerating high-fidelity combustion simulations with classification algorithms that I did with my colleagues Ashwin, Nicholas, and Matthias at Stanford. This work is partially funded by NASA and the Air Force Office of Scientific Research. So a bit of motivation to this work. This work concerns high-fidelity turbulent reacting flow simulations. And these computational tools can be very useful for designing internal combustion engines, gas turbines, or rocket combustors. And these simulations are typically done by solving conservation equations. I'm sure you guys have seen a lot of them today. So in this work, we perform large eddy simulations, which involve solving the filtered conservation equations. And these methods can incur some pretty high computational costs for turbulent reacting flows, mainly because of two reasons. First, we can have a large number of species, which increases the dimensionality of the problem. So a typical methane finite rate chemical mechanism has about 53 species and about 325 reactions. So we would have to have 53 chemical species equations to represent that. And the use of implicit solvers for the stiff chemical source terms can also incur some extra costs from using iterative ODE solvers for these methods. So in combustion modeling, computational costs are typically solved by incorporating some form of dimensionality reduction. So we have 53 chemical species for methane, right? One method of reducing the chemical mechanism is just by picking like 17 or 19 important species to represent the combustion chemistry. Alternatively, another popular method is to incorporate the manifold method, which basically reduces the representation of the combustion chemistry from the independent species to about 2 or 3 model parameters. So we would be solving 2 or 3 chemical species conservation equations instead of 53. The problem with manifold methods is that they're typically only valid for certain regions. In this diagram by Williams, you can see that the flamelet methods are only valid for the upper portion of this regime diagram. Fortunately, a lot of practical combustors do fall into this regime, such as diesel engines, gas turbines, and even some parts of supersonic combustions. But in some operating conditions, these combustors, they don't really operate in this regime. So we kind of have to be smart about using these combustion models. So we know that in certain different operating conditions, different regimes of turbulent reacting flows can basically be modeled by different combustion models. The choice of these combustion models within the domain is really a balance of computational cost and computational accuracy, as can be represented by this Pareto front over here. So typically, domain knowledge from combustion scientists, such as me and my colleagues, are typically required to assign the optimal combustion models. As you can see in this rocket combustor, near the rocket injector, we can represent the flow field over here with 6 different combustion chemistries. So we could rely on domain knowledge, or we could potentially frame this as a supervised learning problem, which is what we've done in this work over here. So the computational method that we use here, as mentioned before, involves solving the large eddy simulation equations. We use a 4th order finite volume solver. We model our turbulence with the thickened flame model and the Smagorinsky models. And the combustion chemistry is represented by a 33 species finite rate chemistry model, a flamelet model, and an inert mixing all in the same domain. So the objective of this work, as I mentioned before, finite rate chemistry is a very accurate but slow method. This is the method that uses the 53 chemical species, or 33 in this case. And the flamelet progress variable is a cheaper model that uses 2 or 3 model parameters. But as you can see in the results over here, it cannot represent thermal boundary layers very well. And so what this means is that it overpredicts carbon monoxide near the walls and it underpredicts the temperature near the wall compared to finite rate chemistry. And this can create a lot of discrepancies if we're trying to model the right materials for our rocket. So we're interested in using machine learning to improve upon the flamelet progress variable simulations to create a equal fidelity simulation to the finite rate chemistry models at a lower cost. And so let's talk about our configuration over here. It's based on the gaseous oxygen, gaseous methane, single element rocket combustor from Silvestri and colleagues. We use a 200,000 cell axisymmetric domain, and the boundary conditions are shown in the figure over here. We have a plot of temperature and velocity. So in our approach, how we incorporate machine learning into this large eddy simulation is that we first take high fidelity finite rate chemistry data. We evaluate the submodel error. I'll go into this into the next slide. And we create labels where to assign inert mixing, flamelet progress variable, as in our flamelet model, and the finite rate chemistry model. We construct our training features using a feature selection tool. What we have is the mixture fraction, progress variable, density, temperature, the Prandtl number, and the scalar dissipation. These are important values in combustion. So it's kind of nice to see that the feature selection tool is able to pick the right features essentially. And then we train our classifier to essentially map the features to the predicted labels, which produces a plot of basically where to assign the optimal combustion model. And so when we construct our training data, our training labels with our training data, we essentially take a normalized error for a quantity of interest. So in this case, our quantity of interest is temperature and carbon monoxide, because as we've mentioned earlier in the previous slides, that the flamelet progress variable method does not model temperature and carbon monoxide in this case very well. So we put a user-defined threshold, and if the normalized error is less than the threshold for inert mixing, so we take finite rate chemistry and we take inert mixing data, we find the error of it, and if the error is less than our threshold, we select that inert mixing model. And if that fails, we then select a flamelet progress variable model, and if that fails, we select the finite rate chemistry. So in the worst case scenario, we use our highest fidelity model, which is also our most costly model. And so this is what our training data kind of looks like in mixture fraction and progress variable space. So mixture fraction basically tells you what percentage of the flow field comes from the oxidizer stream and the fuel stream. And the progress variable tells you how much the fuel has reacted. And we see that in our data, the yellow line over here, or the yellow scatter plots, match really well with the stable flamelet branches, which is what we expect flamelet, the FPV model, to do really well. We see that inert mixing is assigned near the pure fuel and pure oxidizer streams when there is no reaction, which is pretty accurate too. And we see that finite rate chemistry is basically assigned in regions outside of the flamelet branches. So we have some results from our a priori test, which is just by applying our classification algorithm to select models on a single snapshot from an unseen time. We use a random forest with 20 decision trees, and it does a pretty good job. It has about a classification accuracy about 70%, 80%, and it assigns about 30 to 60% in finite rate chemistry. And these figures are pretty speckled. We think it comes from the fact that random forests, we can't really regularize them that well with an L2 norm or anything. So it could come from that. And basically finite rate chemistry is assigned in the recirculation zone over here and near the walls, which is where we expect the flamelet progress variable model to fail. And inert mixing is basically assigned near the fuel and oxidizer injectors, which is expected, and in regions far away from the wall near the oxidizer core. So these different cases use different thresholds, and they use different quantities of interest, just to clarify that. And we repeat the same thing with our neural networks. And we use a 5-layer fully connected neural networks with an L2 norm as a regularizer. And we see that the assignment is a lot more contiguous, which is good because under the hood in our code, to switch between the models, we carry our reconstruction operation. So if the assignment is a bit speckled, like in the previous case, we would have to carry out a reconstruction operation a lot more often, which isn't ideal for computational costs. So again, the classification slightly lower, but still about 60 to 80%. And the finite rate chemistry assignment is pretty similar to a random forest in terms of numbers, but the behavior of it is different because of the regularizing term. We applied our classification method in situ as an online during our LES. And this is just a video showing our model assignment. As you can see in our a posteriori simulations, it still has a similar pattern of assigning finite rate chemistry in the recirculation zone and in regions near the wall, which is where we want them to be assigned essentially. So just a comparison between the random forest and the neural networks. We have time average and instantaneous data over here comparing to both of them. And again, neural networks are a lot more contiguous than the random forest. And the predictions of the temperature and carbon monoxide flow fields are pretty similar to the finite rate chemistry case, which is our high fidelity model. And we've shown that there is a 20% improvement in computational costs when we use this method to reduce the cost of it essentially. So in conclusion, classification can be used to assign well-tested combustion models in a single simulation domain. The overall desired fidelity of where to assign things can be controlled during labeling through our threshold method. Our data-assisted simulations outperform the monolithic flamelet progress variable simulations. And our random forest and neural networks demonstrate similar accuracy, but show different behavior because of regularization. So in terms of future work, we want to explore using more complex deep learning architectures such as convolution and LSTM layers. And we want to include some physical laws and some, some of the physics-informed loss functions.